Welcome back. The last video was about the input files. In this video, we are going to discuss all the important output files which are generated on completion of an ORCA job. Let's try to analyze the output files of the simplest molecule, that is one electron molecule hydrogen ion. And in the theory section, it was discussed in detail the problem of molecular hydrogen ion, where the Hamiltonian operator was created, comprising of the electronic Hamiltonian operator and the potential energy Hamiltonian operator. It's a three-particle system, two nuclei and one electron. And then the molecular orbitals were created by the linear combination of hydrogen 1s orbital. And using the variation principle, we got the energy. We got the ground state energy, and the ground state energy wave function is given by this particular expression, and its corresponding energy is plotted as a function of distance between the nuclei. This is the bonding molecular orbital energy, and that's the anti-bonding. The blue one is the anti-bonding molecular orbital energy. So from this plot, we can compare our theoretical result obtained using 1s hydrogen orbital, which was used to create the molecular orbital. And the two things we normally try to check with the experimental data, and that is one, this dip. This dip corresponds to the bond energy. That's the energy required. In this case, it will be the energy required to break H2 positive ion into hydrogen and H positive ion. And the distance between the nuclei at which that's a dip, the minimum potential energy, that corresponds to the equilibrium bond length between the two hydrogen atoms. And in the next section, in the next lecture, he compared the experimental value. The experimental value bond length is 1.06 angstrom, and the dissociation energy is 2.78 electron volt, whereas the bond length obtained using hydrogen 1s orbital is found to be 1.32 angstrom, and the dissociation energy 1.76 electron volt. So do remember this. I'm going to repeat the calculation using ORCA. So let's first create a hydrogen molecule ion. So go to element drop down menu, choose hydrogen, click and drag. Now we have H2. The first thing we'll try to do is auto optimization, molecular mechanics based. Now what they'll do, they'll change the bond length till which at which the potential energy is minimum and the change in energy becomes zero. So when I click on the start button, you can see that very soon it became D equal to 0. Right? Now we'll use this configuration, you use this structure to make an input file for the ORCA. Let me first click on the stop button. Now, but I want to do the calculation for H2 positive ion. Now in classical molecular mechanics, there is no option to change the number of electrons, but in quantum mechanics, we can do that. So what I'll do, I'll go to the extension menu, choose the ORCA option, generate input file, generate ORCA input. Since we can't create H2 positive ion for the molecular mechanics thing, so geometry optimization for H2 positive ion is not possible using force field. That we can do only by the help of quantum mechanical thing. So what I'll do, I'll optimize this H2 positive ion. So let the comment be optimization, or you can say geometry optimization of H2 ion. H2 ion. That's a comment. So make this a habit to give a proper comment just to know that what this job is meant for. And then what I'm going to do is I'm going to do the geometry optimization, the calculation and geometry optimization using again Hartree-Fock method. But by default, they have chosen restricted Hartree-Fock. But this is not a closed shell molecule. All the electrons are not paired. It is a one electron system and that is unpaired. So the charge, let the charge be +1. Now it has become proper H2 positive ion. And then the multiplicity. Now since it has one unpaired electron, so total spin multiplicity will be 2s plus 1, that is 2 into half plus 1, that is doublet. So make this multiplicity 2. And then let me change this basis set and make it simple STO3G. Let me see what is the bond dissociation energy and the bond length we are getting after the geometry optimization of H2 positive ion at the level of restricted Hartree-Fock, but this is going to be unrestricted Hartree-Fock because that's a unpaired electron, that's an open shell molecule. It has an unpaired electron. And then generate. And let me save this in one of the folder which I have created on my desktop. And let me name this as H2 then dash ion. And let's save that in the desired folder. Let me close this. Minimize this. Minimize this. And let me open the command line. So I'm already in the H2 ion folder. So let me check if I have my file there or not. What I'll do, I will put the command dir, enter. Yeah, it's there. The input file is there, h2-ion.inp. INP is the extension name for the input file. In the last lecture also, we said that .inp or .text you can use for text is .txt. Now, let me minimize this and simultaneously let me open the desired folder also so that we can see that what's happening in that particular folder, that particular directory simultaneously. And then let me give the command. What is that command? ORCA, then space, channel 2, greater than sign, space, and then the input file name. So simply I type H and then press the tab button, h2-ion.inp space. Oh, I made a mistake. ORCA. After ORCA, then we have to give the input file name. So H2, then a space, and then greater than sign, then a space, and then again the output file name. Let's name this as the same with the same name, but extension out. Now, if I click this, so it's running, and you can see that lots of temporary files are getting generated during the course of calculation. And once now it's done. Once it got completed, the temporary file vanishes away and you are left with all the important files there. Now, let's try to analyze these output files. So many output files, but the most important one is the second one with the extension name .gbw. H2-ion.gbw. GBW stands for geometry, basis set, and wave function. So this particular file has a detailed information about the geometry of the molecule, the final optimized geometry, then the final basis set. Because using the basis set, in this case we have provided STO3G basis set. What the software do for that molecule which we have created, and at a particular geometry, they create a typical wave function, the wave function with the lowest possible energy for that particular system. So if, for example, if I have bases like phi 1, phi 2, phi 3 base, that is functions, then they'll make it as A phi 1, B phi 2, C phi 3 linear combination. And they'll vary the value of A, B, C so that the final wave function has the lowest possible energy. This is something called SCF, self-consistent field method, by which they keep on changing the coefficient so that the final wave function has the lowest possible energy. But this particular file we can't see because that's in the binary form. If I want to open this, let me see that. If I want to open this, we won't be able to read anything. Let me open this in the Notepad++. That's what you can see there. That's because it's in the binary form, so we won't be able to see what's written there inside this particular file. But note this is the most important file. In the binary form, it has all the information, and this is generally required. If I use the final output file, if I want to use the final optimized geometry, the final wave function for some additional calculation. So I don't need to re-optimize the geometry. I don't need to re-optimize the wave function. I can use the final wave function and the final geometry for some further calculation using this .GBW file. And now the second important one, which you can open and see all the details, is the output file. That's the fifth one. That's the output file. This one. So let me open this in Notepad++. That's there. Now, top, the name of that software, ORCA. It is software for doing ab initio, DFT, and semi-empirical electronic structure calculations, developed by Frank Nesse Group from Max Planck Institute, Germany. Then they name all the persons who has contributed to the development of this particular software. Some specific what they have done for this particular software. So the name of that, for example, Daniel Aravina has contributed for calculating magnetic susceptibility and many names. So thank you to all these developers for giving us chance free of cost to do all the possible calculations. Don't need to worry about how the programming was done. Then they're also grateful to, because they have landed, their program for them. They can use a part of their program. So they're acknowledging that also. Then for doing calculation, they will be using some important mathematical packages. For example, in this case, for 2 electron integral calculation, that's one of the toughest job which is done during the course of the reaction, during the course of that calculation. That is the computation of 2 electron integrals, and that is done by libint2 library. And then another library is this libxc version there for some other further calculation. And then you can see that this ORCA version uses C-BLAST interface for vector and matrix operations. LAPARC interface they use for linear algebra routines. So every software use different mathematical packages, freely available mathematical packages. And if they get access to that, then they acknowledge that those groups for providing them that access. And then we had used STO3G basis set. That's the basis set came from the John Pople group. John Pople got the Nobel Prize, 1998 Nobel Prize for developing these computational methods there. So the original basis set from John Pople group, the two important softwares which are paid software, Gaussian and Spartan, they are from that group only. W. Harry is still he's the director of that company Spartan, one of the most widely used software, especially in the industrial field there. So the STO3G basis set for hydrogen to neon was developed in 1969. Then from sodium to argon was developed in 1970. And that's the name of the paper also. So if you want to see that detail, how they did that, visit these papers. The information about the paper is given there. And then warning, what they're saying, your system is open cell because it has unpaired electrons. That's why the system is open cell. Since by default you choose restricted Hartree form, we chose that restricted Hartree form. Now they're shifting to unrestricted Hartree form. Oblique they give because that's a ConSem DFT. We are not in DFT calculus. If it is DFT, then it is ConSem, restricted ConSem and unrestricted ConSem. Right now we have chosen Hartree form, so that's why it is shifting from restricted Hartree form to unrestricted Hartree form. And then geometry optimization. Then the input which we gave initially, and that was our input file. That's the information about the input file. And then in this particular job, we are going to do geometry optimization. So what do we mean by geometry optimization? What they'll do, in this case, there's only one bond. But if there are many bonds, there'll be angles, dihedral angles. So they will change the bond length, bond angle, and dihedral angle, and will try to get a particular geometry which has minimum force on each atom. Minimum means nearly zero force on each atom. So that will correspond to the stationary states. Fine. So the minimum force, that's a criteria they have made. What is how they'll decide that it has converged, how they'll decide the optimization has taken place. So that they decide on the basis of, the computer decide on the basis of energy change. If the total energy change between the adjacent variation is less than 5 into 10 power minus 6 Hartree. Hartree is the atomic unit of energy. EH stands for Hartree. 1 Hartree is 27.2 electron volt. That's one criteria. Second criteria is maximum gradient to the energy. So energy upon the coordinate, that is nothing but, you know that force is what? dE by dx, that's the force along the x-axis. So F is minus dE by dx, so that energy, its unit will be this gradient stands for force. Gradient of energy is force. So if the maximum gradient is below 3 into 10 power minus 4 Hartree per Bohr, or the root mean, and the root mean square gradient means considering all the atoms, then it should be below 1 into 10 power minus 4 Hartree per Bohr. Another criteria they do it, displacement. Because if there's force existing on a particular atom, it will get displaced. So if there is minimum force, there will be minimum displacement. So if the maximum displacement is below 4 into 10 power minus 3 Bohr, and the root mean square displacement, considering all the average value of that atoms there, it should be below 2 into 10 power minus 3 Bohr. So that's the criteria they have laid down for deciding whether the geometry optimization has taken place or not. Now they write strict convergence false, means you can apply that, means you have to follow all these 5 conditions only. When all the 5 conditions will be fulfilled, then only we'll consider geometry optimization has taken place. Even if there's 5 has taken place and 1 is very close to that, then again you can see that it has the geometry optimization is done. So they decide, the software itself decide, and that's why they have written false. Even 4 of them, 4 of the condition has been fulfilled, 5th one is very close to that, we'll consider that to be final geometry optimization has taken place there. Okay, so let's go down. Then internal coordinate, remember in the last lecture we discussed this. Number of bonds will be n minus 1, number of angles will be n minus 2, and the number of dihedral angles will be n minus 3. Here, number of atoms is 2. So number of bonds will be only 1, 2 minus 1, 1. No bond angle, no dihedral angle, so only bond length between one edge and another edge. Look at that. In ORCA, there's one thing you have to remember. In most of the software, the numbering will start from 1, 2, 3, 4. But in ORCA, every time the numbering starts from 0. So to one atom, they assign the number 0. To another atom, they assign the number 1. So between 0 and 1 atom, means 0 is one hydrogen atom and 1 is another hydrogen atom, the bond length is 0.708. So right now, they have taken 0.708 angstrom. And the total doubly differentiated their energy. So number of atom is 2. Degree of freedom, in this case, degree of freedom is only 1. Now they are starting the geometry optimization. So that's the starting value of the bond length. So during the geometry optimization, this bond length will change. So you will see that right now the value is 0.708. Now, then they convert this. They have written again the coordinates in the form of Cartesian coordinate, x, y, z coordinate. And then using this also, if you check the bond length, you'll get this value only. They convert that Cartesian coordinate into internal coordinate. So you can see that internal coordinate is 0.708. And they have extended the decimal place. Again, the same internal. Now, this is in angstrom, and that's an atomic unit. Remember, one atomic unit is 0.529 angstrom. So if I divide this by 0.529, if I divide this by 0.529, you'll get this particular value, 1.337. Fine. And if you multiply this with 0.529, you'll get this particular value. So that's a conversion of atomic unit to angstrom. Length, one atomic unit is 0.529 angstrom. Now the basis set information. We had taken STO3G basis set. STO3G basis set means we have used 3 Gaussian functions to mimic a Slater type orbital. In this case, the Slater type orbital is 1s type orbital. 1s type orbital we are mimicking by the help of 3 Gaussian functions. That's why the name they have written 3 Gaussian functions, that is 3s, Gaussian type S, contracted to 1s, that is Slater type S. Fine. So that's the group 1. For both the hydrogen, they have used the same group number 1. That's this particular thing. Now, the complete statistics of this basis set is given. Primitive Gaussian cell, primitive Gaussian function, look at that, total 6. 3 for each hydrogen atom. 3 for hydrogen atom number 0 and 3 for hydrogen atom number 1. Using 3 Gaussian functions, they are creating one Slater type orbital. Since there are 2 hydrogen atoms, so total Gaussian functions used are 6, and total basis function. Each basis function, we are terming that as contracted Gaussian type orbital. So total contracted Gaussian type orbital is 2, 1 each for each hydrogen atom corresponding to 1s type orbital. Okay, now they are doing internal evaluation. Since you have a molecule, so you know the position. Right now, this position is 0.708 angstrom, and then you can do all the integrals there. Integral means 1 electron integral, 2 electron integrals, and that's what they're doing using the mathematical package which they are using in this particular software. And they did that, and all those values are saved in any temporary file. That's why in the process, lots of temporary files were created. So those were saving this 1 electron integrals or 2 electron. In this case, there is no 2 electron integral because there is no there is only 1 electron. There won't be any 2 electron integrals, only 1 electron integral. But once you have more than 1 electron, you'll have also 2 electron integrals values there. Okay, now there's safe setting starts there. At each geometry, they will try to get a proper combination of the input basis function. So they are doing that, all that calculation using some method called DIIS, direct iterative internal space. That's what they say. That's one of the way to do the wave function optimization. So at each geometry, there'll be self-consistent field, SCF type down there. They'll change the coefficient and try to get the basis function, try to get the total wave function with the minimum possible energy. That's all the technical terms there. And let's go down. And you can see that initial guess done, that was done in 0.1 second. You can see the time. and only in one iteration. This 0 is number one. You can say that because in ORCA everything starts from 0. In single cycle, they have optimized the basis function because the basis function we chose was very simple. You can see that if you use more number of functions there, then it'll have more cycles. More cycles will be required to do the optimization of the wave function. So SCF done. Right now, they are saying that the energy of H2 positive ion is this many electron volts, minus 14.29 electron volt. But you'll see that there will be continuous decrease in this particular energy once the optimization process moves there. So that's step one. Now we'll talk about this analysis at the end. Then geometry process is going on. Look at that. One step they did, and they calculated the force. Right now, this is the tolerance value, which we discussed earlier. Right now, that's the value, much higher than the tolerance value. That's why none of them has converged. So no, no, no. We want all of them should be yes. Fine. Let's go down. Now what they have done, they have changed the bond length slightly. The bond length, they have decreased the bond length. And then they repeat the same cycle. They repeat the same cycle. Again, they do the SCF convergence. And then look at that value. It has changed. But still, there is no, no, no. So this cycle will keep on repeating and keep on going down. We'll see continuous decrease in the summary is given in another file. We'll check that summary, means how in each step the energy changed. And then go down, go down. So let me go directly at the end. So same thing is repeating. Same thing is repeating because at this point you can see that out of 5, 3 of them has converged, not the top 2. Energy change and the force that is root mean square gradient, that has not converged. So the optimization has not yet converged because they have written that the optimization has not yet converged. More geometry cycles are needed. So again go down, again go. So what they're doing, they're changing the bond length and then looking at the energy, SCF conversion. Oh, done. Good. So done. All the 5 got converged. There's yes, yes. This is what you want to see at the end, and that's what. Hooray! Just once they get that 5, this is the sign they flash. The optimization has converged. And then they'll provide you all the information, final information. And that final information is the bond length. And they're saying that in internal coordinates, the bond length is 1.06 angstrom. Let me see what was the experimental value. So we started with H2. We started the H2, and now let me see what was the experimental value. And the experimental value is, oh, perfect. So using hydrogen 1s orbital, the bond length was found to be 1.32 angstrom. Experimental value is 1.06 angstrom, but using STO3G, what we have got is again 1.06 angstrom, exactly matching with the experimental value, very close. And second thing we'll try to do is the energy matching. Let's go down. We'll have more information. So one bond length is matching with the experimental value. Let's talk about the energy. This is the complete information about the energy. Final, after optimization. The final energy is minus 15.85 electron volt. This is the energy of H2 positive ion. Minus 15.85 electron volt. They have partitioned that. Partitioning is out of this minus 15.85, there will be nuclear repulsion between the nuclei, potential energy, that is 13.57. The electronic energy, this electronic energy is sum of kinetic energy of electron and nucleus electron interaction. So this electronic energy is partly kinetic, partly potential energy. Potential energy due to the attraction. Kinetic energy will be positive and the potential energy in this case, because of nucleus electron interaction, will be negative. So total is minus 29. Out of that, since there is only one electron, there will be one electron energy minus same value. There is no two electron energy because there is no repulsion. But once you have a system with more than one electron, there will be a two electron energy, and that value will be in positive because that's repulsion. Again, they have partitioned on the basis of vibration energy, that is potential energy and kinetic energy. So potential energy, you can see that it is minus, if I sum the top these three, you'll get the same value. Also, we can, if you sum these two, also you get the same value. This kinetic energy is part of this electronic energy. That means if I sum this with the negative side, minus 29.43307 is equal to kinetic energy, this plus potential energy due to nucleus electron interaction. So that means the nucleus electron interaction will be minus 29.43307 and minus 15.83. That means some value around 40, minus 45 will be the potential energy interaction, potential energy due to the nucleus electron interaction. And then you sum the kinetic energy and this nuclear repulsion, again you will get that value minus 15.8. So total potential energy, this value is actually sum of this nuclear repulsion one and the component which is present in this particular electronic energy, that is nucleus electron interaction term. That's the total potential energy, and then there's this kinetic energy. So final, if I sum these two also, you'll get this particular value. Then, okay. Now, regarding the population analysis. What do you mean by population analysis? That we discussed, that has been discussed in this particular module itself in the theory section. Population analysis method, what they do, they partition the electron density between the nuclei so that each nuclei has a number of electrons associated with it. Number of electrons associated with it. That number is not necessarily an integral number. That could be in some decimal thing there. That's because, and we know that there is no quantum mechanical operator for the atomic charge. And so these partitioning, these methods are all arbitrary. That means there could be more than one different method. Different method employ different technique to do this analysis. One of the frequently used one is the Millikan population analysis. Others are Lawton population analysis. Alternatives can be there's AIM, that is atoms in molecules, Bedder's theory. Then NPA, that is natural population analysis. In Millikan population analysis, we must have go through the theory section in this particular module only. They discuss that in detail. You calculate the charge on any nuclei on the basis of matrix, electron matrix density. That's a very important thing, and that normally we get that value once we do the SCF calculations. After SCF calculation, the calculation of Millikan population analysis is very trivial, and also we use overlap integral. One of the issue with the Millikan population analysis is normally in some cases, in some extreme cases, we get a negative number of electrons in an orbital having negative number of electrons. So qualitatively, because they say that that's impossible. You can't have a negative number of electrons. But in some cases, using this molecular Millikan population analysis method, you get negative number. And sometimes also in a particular orbital, you get number greater than 2. That's completely violation of Pauli's exclusion principle. According to Pauli's exclusion principle, an orbital at the maximum can have 2 electrons. But in some cases, after doing Millikan population analysis, value gets slightly greater than 2. So that's the issue with the Millikan population analysis. This Lawton population analysis avoids problem of negative populations or populations greater than 2. And most of the quantum chemists prefer Lawton than the Millikan because that is very close to, and that is also some independent of the basis set. Means they're not sensitive to the basis set. So you can check this. You can check as an assignment. You can do this assignment because in theory section, some of the molecule has been taken as an example, and he did that Millikan population analysis and Lodin population analysis. Try to use the same molecule and you do it yourself using ORCA, using different basis set, and see how close you get your value as which has been discussed in the theory part. And then you can also calculate bond order. Again, bond order, there is no quantum mechanical operator for bond order. It's bond order, just like atomic charge, is not a quantum mechanical observable. So there are different methods. One of the most important popular method is this Mayer population analysis. And you can see that using Mayer population analysis, the bond order in H2 positive is having electron 1. So remember that MO theory, you have the formula half NB minus NA. So number of electrons in bonding is 1, so half into 1 will be 0.5, and that's what you're getting here, 0.5. Right? And they're also doing their spin analysis. So total number of unpaired electron is 1. By default, ORCA also calculate the dipole moment. So in this case, the dipole moment of H2 is a linear molecule, and both the side we have H and S. So the total dipole moment has to be 0. So it is a dipole moment is 0. But every time by default, when you do the electron research calculation using ORCA, you'll get the dipole moment, and that's what the final ORCA terminated normally. This is one of the message you want to see once you submit a job. That means the job getting completed without any error. Also, in addition to the comparison of bond length with the experimental value and with the value which we got using hydrogen type orbital, let's try to compare the bond dissociation energy with the experimental data. For that, let's go to the table, this one. The total energy we got in this case using STO3G basis set is minus 15.85 electron volt. In heart rate is minus 0.582. If you want to convert heart rate to electron volt, you have to multiply with 27.2. So the total energy electron volt in this case is minus 15.85, or you can say approximately minus 15.86. And this is the energy of H2. When it gets dissociated, it converts to hydrogen atom and hydrogen ion. Electronic energy, there is no electron in the H positive ion, so no electronic energy. There is one electron in hydrogen atom, and we know that hydrogen atom electronic energy value is minus 13.6 electron volt. So moving from minus 15.85 or minus 15.86 in this case to minus 13.6 electron volt when it dissociates. So difference, that is minus 13.6 electron volt minus of this. So it will be around, that is plus 15.86 minus 13.6. So approximately it will be 2.2 electron volt. So using this data, approximately we are getting the bond dissociation energy equal to 2.2 electron volt. Again, repeat, how we got that? The energy of dissociated H and H positive minus energy of this. Energy of dissociated H and H positive is minus 13.6. Energy of this H2 is this much. So minus 13.6 minus of this value. So that is approximately 2.2 electron volt. And if we compare with the experimental result, it is 2.78 electron volt. So not that good, but yes, it's better than the hydrogen orbital, which we had used in this case. So it has moved from 1.76 to 2.2. So 2.2, approximately the difference of 0.5 electron volt still exists. We can better the result if you go for a better choice of basis set that for you to compare. So that's for today's session.